Oscilloscopes are measurement tools designed to faithfully represent a wide variety of signal parameters. But oscilloscopes are only part of a measurement system, a system that includes the oscilloscope, the circuit and signal under test, and a means of getting the signal to the oscilloscope. It's that last consideration that we usually take for granted, even though the right or the wrong method vitally affects the use and accuracy of the entire measurement system. Oh, I'll concede it may seem trivial. Circuit under test here, oscilloscope there. Question: how do we get the signal to the scope input? Well, the obvious answer is a microhook and a wire. Clever and resourceful, eh? Amazingly enough, it'll even work if the signal is DC or very low frequency and we don't pick up stray EMI. All we add is the resistance, which hopefully is known, of the wire to the circuit. But as we go up in frequency, we add parasitic strays around the resistance until we get this, a marvelously skewed waveform that's part signal, part transmission line effect, and part country and western station, faithfully graphed versus time by the oscilloscope. Or we could try the other obvious answer and try one of these, an oscilloscope probe, a device designed, like your oscilloscope, to minimize signal loading and distortion. If an oscilloscope is the most versatile and widely used electronic measurement tool, then probes are the most overlooked and misunderstood measurement tools. Transferring signal information from your circuit under test to your oscilloscope can become the weakest link in your measurement chain, skewing your results in seemingly arbitrary ways. On the other hand, probes understood and properly used will enhance virtually every measurement. Our discussion of probes and signals will be in 5 parts. This section is about the need for probes. The next 3 sections examine passive, active, and current probes and how they work. The last section reviews probe selection. Along the way, we'll demonstrate some measurement techniques that you may find useful. To begin, we need to measure the signal under test, not transmission distortion, nor the effects of circuit loading. In other words, yes, we need to use a probe. The real question is which probe? Now, ideally, a probe is a device that transfers signal energy without distorting the signal or its source. And this probe is typical, a small, handy device made of gray plastic. It includes 1.5 meters of cable, shielded to reduce external fields. It comes with a variety of adapters for different applications. Oh, great, you say. Now I have a probe, and all I have to do is use it, right? Well, no. Remember, I define probes ideally. As you know, in electronics, nothing behaves ideally. Even probes will load the circuit and distort the signal to some degree. But all probes are designed to minimize signal loading, and different kinds of probes will load the signal less than others in different situations. Why are there different kinds of probes? Because there are different kinds of applications. To minimize loading and distortion, and to provide utility for those different applications, probe designers followed 3 major strategies and developed 3 basic kinds of probes: passive voltage probes, active voltage probes, and current probes. Each type has different characteristics and offers different trade-offs with an ideal probe. And there are many different variations within each type. Currently, Tektronix makes more than 40 different probes. The problem is not merely how to use a probe correctly, but how to know which probe to use correctly. To understand how to select a probe, we need to consider the entire measurement system. We need to examine the oscilloscope specifications, the probe specifications, the test circuit itself, and the signal characteristics. Now, I'm sure you're well acquainted with scope specifications: input capacitance, input resistance, and bandwidth. But how do they define measurement accuracy? Well, take bandwidth, for example. It specifies where the system response is down 3 dB, or to 0.707 of the initial amplitude. Let's say that you have a system with a 350 megahertz bandwidth, and you need to make an amplitude measurement accurate to within 3%. What's the fastest signal your system can measure and keep within specs? If we consult a graph of bandwidth versus amplitude accuracy, we see that a 350 megahertz system is accurate to 3% for only 3/10 of the bandwidth, or 105 megahertz. The general rule is, as you increase frequency, the amplitude accuracy of the system decreases. And that assumes you haven't done anything to degrade the effectiveness of your measurement system, such as using a probe with too little bandwidth. What are probe specifications? They may seem a little unusual. Key ones are attenuation, input resistance, input capacitance, input impedance, maximum non-destructive input voltage, bandwidth, and aberrations. Attenuation describes the ratio of voltage in to voltage out for the probe, usually 1x, 10x, or 100x. Probes that are called 10x, for example, will attenuate the signal by a factor of 10. Attenuation will affect the range of voltages that the system can measure. Input resistance is the Rin of the probe. It determines the probe's DC loading to the circuit under test. Input capacitance is the Cin of the probe. It determines the probe's high-frequency loading. Input impedance decreases as frequency increases and is usually shown as a graph. Maximum voltage is a safety specification that must not be exceeded. Again, it's displayed as a graph because the probe's ability to withstand voltage decreases as the signal frequency increases. The last two, bandwidth and aberrations, are related. What are aberrations? They're a measure of how closely we can get the real world to the ideal. Specifically, probe aberrations are deviations from an ideal step response on a specified scope. A typical probe might have an aberration specification of plus 4%, minus 6%, and 8% peak to peak. This means that the step response of that probe will first not exceed plus 4% or fall below 6% of the final value, and second, that there won't be more than an 8% error from the maximum overshoot to the maximum undershoot when used on a scope with a specified bandwidth. That's important. Oscilloscopes and passive probes should be carefully matched in bandwidth. For example, this is a 100 megahertz passive probe. It's designed to be used with a 100 megahertz oscilloscope. Now, if I insisted on using it with a 350 megahertz scope and viewed a fast rise time signal, the aberrations would be increased because the lower bandwidth probe was not designed to control the high frequency components of the faster input signal. Much like the grain of a photograph would increase as we used higher magnifications. If you think about it, probe bandwidth specifications don't mean much without aberration specifications. So, if you're going to view fast signals on a high-speed scope, use a high-speed probe. By matching those general probe and scope specifications, you'll create a system that does not degrade the performance of either component. Is that all there is to it? Well, no. As you'll see in later sections, specific kinds of probes may have additional specifications to consider. And we've only examined oscilloscope and probe specifications. What about the test circuit and the signal characteristics I mentioned earlier? For example, why is test point impedance an important consideration? Or the DC offset voltage? Or signal amplitude and bandwidth? The reasons that these are so important is the same reason there are so many probes. And to understand that, we need to know more about the different kinds of probes. There are three general types of probes: active, current, and passive. Passive probes are the most common. The probes that came with your oscilloscope, for example, probably were passive probes. They are cost-effective over the broadest range of applications. In the next few minutes, we'll discuss the major kinds of passive probes, find out why they work the way they do, and hopefully discover how to use them better. They're called passive because they contain only passive elements: resistors, capacitors, and inductors. Their design has a lot of advantages. The highest bandwidth probe Tektronix makes is a passive probe. Passive probes don't require any additional power source and are very easy to use. They're the lowest cost of all probes that reduce circuit loading. There are several different ways to classify passive probes, depending on your need. You can divide them by their impedance characteristics, low and high, which we'll do a little later. Or you can group them by their attenuation. Most passive probes reduce circuit loading by inserting a series impedance into the signal path. This increases the input impedance at the probe tip, but unavoidably attenuates the input signal as well. Now, usually this isn't a problem. But there are applications when lowering the sensitivity of your measurement system isn't an option. Suppose you needed to view a 60 Hz low amplitude ripple on a power supply output, for example. At a 1 or 2 millivolt signal amplitude, the attenuation of a 10x probe becomes intolerable. The simplest kind of probe has no attenuation. A 1x, or non-attenuating probe, is an improved version of the wire we originally tried. It's basically a length of EMI-shielded, low-capacitance cable, about 8 picofarads, or puff, per foot, that connect the circuit and the scope input. This design has a good high Rin, the scope's 1 megohm. It's the choice for viewing low-amplitude, low-bandwidth signals. But if you needed to measure a 20 megahertz signal on the collector of a transistor amplifier, what then? Now remember that most probes use attenuation to reduce circuit loading, while a 1x probe, by definition, has no attenuation. Will the 1x probe significantly load this circuit? We'll start by observing the intended output of the circuit, a sine wave. Now we'll add our 1x probe to the circuit, and the circuit output changes. Our sine wave has become attenuated. Why did our 1x probe change the circuit? Look at the schematic. To the scope's capacitance of 20 puff, we need to add C cable, which might be 40 puff or 5 feet of 8 puff cable. The total C in is 60 puff, more than enough to load most sources significantly at high frequencies. In our example, adding 60 puff to the transistor's collector was more than enough to change the circuit's gain and bandwidth characteristics. Conclusion? A simple 1x probe is only good for low bandwidth applications. Attenuating passive probes are much more versatile. As I said, there are two major families: high impedance or high Z probes and low impedance or low Z probes. Some passive probes are even dual purpose with both 1x and 10x attenuation settings. An attenuating passive probe is basically an extension of the oscilloscope's attenuators. It forms a voltage divider between the series impedance in the probe and the input impedance of the scope. For example, if we add R2 to R1 and both R1 and R2 are equal, then V out will be half of V in, a simple voltage divider. Is that all an attenuating probe is? Well, no. This is only true if V in is only DC. As frequency rises, the parasitic capacitances around each of the resistors changes the attenuation factor. This is really a model of an uncompensated high impedance probe. We can overcome the strays by adding external capacitors. If the low frequency attenuation ratio is the ratio of the resistors, then the high frequency attenuation ratio is the ratio of the capacitors. By adding external capacitors, I can control the ratio of capacitors and make the attenuation the same over all frequencies. The RC time constant on one end will equal the RC time constant on the other, creating a compensated voltage divider. Which is why we should never use a high Z passive probe until we've compensated it. What do we do when we compensate a probe? What's so important about tweaking up a square wave? Well, how important is your measurement? Until you make a compensation adjustment, also called low frequency compensation or LF comp, and get a flat square wave response on the calibration signal, you can't be sure that your passive probe forms a compensated voltage divider. If we look at a simplified model of a 10x or attenuating passive probe, we see its 9 megohm resistor and the 1 megohm resistor in the scope input. It looks a lot like our voltage divider, functioning as a 10x voltage divider at DC. The difference is a capacitance shunting the probe resistor. Now, a square wave contains all odd harmonics above its fundamental. When we adjust the capacitance of the probe to firm up the square wave, we're effectively flattening the frequency response of the probe. The probe becomes a frequency compensated voltage divider as R tip times C tip becomes equal to R scope times the sum quantity of C scope plus C probe. If we don't compensate the probe, our attenuation will change with frequency. If the probe is undercompensated, there will be too much gain at high frequency. If the probe is overcompensated, there will be too little gain. Either way, you're left with a measurement that may or may not be accurate. As we go up in frequency, the capacitive input characteristics of the probe change in other ways that can be important when we select which probe to use. First, the input impedance of the passive probe decreases with frequency. 10 megohms at DC may drop to 120 ohms at 100 megahertz, greatly increasing the circuit loading. Second, the maximum input voltage also derates with frequency. The probe absorbs more energy as its input impedance drops, and the probe that started off at a 500 volt rating may only be able to withstand 50 volts at high frequency. Why will an attenuating probe work at higher frequencies than a 1x probe? Take a 10x high Z or high impedance probe, for example. It consists of a 9 megohm tip with a 12 puff shunting capacitor working through a cable into the 1 megohm resistance and 20 puff capacitance typical of a scope input. The cable is a resistive center conductor coaxial transmission line. The resistance is 39 ohms per foot. The capacitance is 8 picofarads per foot, and the characteristic impedance is 170 ohms. The resistive or lossy nature of the cable lets it be terminated into a capacitive load with optimal transient response. This section is a compensation box at the scope end. It forms a termination for the lossy cable. LF compensation is correct when R tip times C tip equals R scope times C scope plus C cable plus C LF comp. These components help terminate the transmission line cable. The 60 nanohenry inductor provides inductive peaking, which improves rise time. The 200 ohm variable resistor provides a first-order resistive termination, which hides the scope input capacitance from the cable. This 500 ohm variable resistor, in series with CLF comp, forms a peaking circuit to adjust the probe's front corner flatness. What's the total effect? Reduced loading. Rin equals R probe plus R scope, or 10 megohms. Cin equals the series combination of C tip and C probe plus C scope. Since series capacitors add like resistors in parallel, C tip places a limited value on Cin. Using the formula, we fill in the blanks. For a Cin of less than 11 puff, less than the Cin of the scope, and 49 puff less than the Cin of the 1x probe. Now, this circuit is typical of a simple 100 megahertz high Z passive probe. Higher bandwidth probes use more complicated termination schemes and more adjustable components to adequately control transient response, but the guiding principles are the same. So with your trusty high Z probe, you're ready for anything, right? Well, not exactly. Impressive as high Z passive probes are, they do have limitations. If you need to measure the rise time of an ECL gate and apply the same high Z probe, you may find a much slower rise time than you expected. As we'll see, high Z probes are not the best choice for fast rise time measurements. Here's another kind of passive probe, a low Z passive probe. It uses low-loss 50 ohm cable instead of the high Z probe's resistive cable, and a 50 ohm scope input instead of the high Z probe's 1 megohm. Basically, there's a 450 ohm resistance in the probe and 50 ohm resistance in the scope. The interesting part is that it forms a 10x voltage divider for all frequencies, because according to transmission line theory, all the 450 ohm tip resistor sees, looking into the terminated cable, is a pure 50 ohm resistance, no inductive or capacitive components. No LF compensation is necessary because this probe is not a capacitive divider. No, that capacitor in the tip is not part of a divider. It's a peaking network to compensate for skin effect losses in the cable at very high frequency. The C-in of this probe consists primarily of parasitics present in the mechanical geometry of the tip. Remember, nothing's ideal. It's actually quite low, about 1 puff. Now, you might say, what a dandy probe. At last, something I can use all the time. Sorry. Remember, the R-in is only 500 ohms. What happens if I attach a 500 ohm probe to a typical transistor amplifier? If I attach the probe to the emitter, circuit operation won't change greatly because a transistor emitter is a low impedance point, usually less than 50 ohms. But if I attach the probe to the base of the transistor, the addition of the 500 ohm R-in of the probe shunts the bias circuit of the transistor, significantly changing the voltage at the base. Remember that I said the circuit under test and the signal characteristics play a big part in probe selection. We have to look at the impedance of the probing point. It's generally okay to use a low Z probe if the source impedance of the test point is 1/10 the R-in of the probe. Otherwise, we'll change the circuit impedance by more than 10% when we attach the probe. Remember, to accurately use a 500 ohm probe, look for a test point impedance of 50 ohms or less. It's with high bandwidth circuits that another problem becomes apparent: ground lead inductance. This is a model of a 10x high Z probe attached to an ideal source. We have the R-in of the probe, 10 megohms, R source, and the C-in of the probe, 11 puff. And we have the inductance of the ground lead. The ground lead L and input C form a series resonant circuit with only R source for damping, which isn't much. When we hit the circuit with a fast pulse, it's going to ring. This is our measurement system response without ground lead inductance. I'm using a probe tip to BNC adapter, which provides a low inductance connection for probe testing and calibration. But if I attach a 6-inch ground lead, we get a much different picture. The 6-inch lead adds an inductance of about 150 nanohenries and creates a resonant circuit with C-in of the probe. We can calculate the resonant frequency of an LC circuit as 1/2 pi times the square root of the ground lead inductance times the capacitance in of the probe. In this case, the resonant frequency is 140 megahertz. A shorter 3-inch lead will give us some improvement, less inductance, and a higher resonant frequency. But here's a low inductance Z lead. To install it on the probe, unscrew the ribbed tip cover and slide it off the ground collar and lead. Now reverse the ground collar and reinstall the tip cover. Now you can attach the low inductance lead itself. The signal with the Z lead is much closer to ideal. Ground lead inductance falls to 30 nanohenries, which raises the resonant frequency to 267 megahertz, which is much more likely to be outside your area of interest. Now, if you don't ground it at all, you get this. Pretty, isn't it? The moral: grounding probes is important. Keep your ground lead short. If that's not possible, reduce input capacitance of the probe by using a low Z passive or an active probe. Okay, we've examined passive probes in theory as well as compensation and ground lead inductance. Now let's examine the effects of attaching some real-life probes to a real-life circuit. Our test signal is a 50 ohm source driving a 20 puff capacitive load. The time constant of the RC network will determine the 10 to 90% rise time. That's 2.2 times RC, or 2.2 times 50 times 20 puff, or 2.2 nanoseconds. First, we'll try a 10x high Z passive probe. Attaching the probe adds its input impedance to the output of the signal source. This loading changes the operation of the circuit. The capacitors in parallel add directly and form a new equivalent C of 31 puff. The Rin of the probe is so high compared to the source R that we can ignore its effect. The new equivalent circuit has a rise time of 2.2 R times C source plus C probe, or 3.4 nanoseconds. Before we added the probe, the rise time was 2.2 nanoseconds. Adding the probe increased the rise time by 55%. Now, if you weren't anticipating this side effect of probe loading, you might assume your circuit was underperforming when you changed the circuit yourself by adding the probe. Another interesting result is that there isn't any voltage divider effect between the source and the probe because of the high input resistance of the probe. This means that our amplitude measurement will be 100% accurate. Conclusion: high Z passive probes are excellent for amplitude measurement, but can create significant rise time measurement error because of their high Cn. Now let's try our luck with a low Z 10x passive probe. Again, we attach the equivalent input impedance of the probe to the circuit. Again, C probe and C source add directly, but this time C probe is only 1 puff. R probe, however, is only 500 ohms, not enough times larger than R source to be ignored. This R probe does form a voltage divider and reduces V out to 0.909 of V source. The capacitor now sees an equivalent resistance of R probe in parallel with R source, creating a new lower R source of 50 in parallel with 500 or 45 ohms. Our new equivalent circuit delivers a rise time of 2.2 times 45 times 21 puff, or 2.08 nanoseconds, faster than the rise time without the probe. Can you improve a circuit just by adding a probe? Well, not really. Remember, you paid for this increase in rise time by decreasing the amplitude by almost 10%. What have we just shown? That no passive probe can deliver the perfect blend of low capacitance and high resistance that would make all measurements accurately. Instead, we're faced with a choice. If amplitude accuracy is crucial, then high Z passive is the best choice. If rise time accuracy is more important and your circuit can stand a 500 ohm shunt to ground, then choose a low Z passive probe. If you need both, stay tuned. If high Z and low Z probes are effective in so many applications, why do we need any other kind of probes? Your answer is that you may not, but let's suppose you have a problem that's a little different. What if you needed to make a measurement on a high impedance, low amplitude, high frequency circuit? A low Z passive probe might be a good choice. It has the low input C that we need, but the comparatively low resistance it offers will pull the circuit point to near ground, unbias the circuit, and destroy its gain. The high Z probe, yes, that offers higher resistance, but its high capacitance will excessively load the circuit and limit its bandwidth. And even if you could accept that, both probes attenuate the already low voltage signal, degrading the sensitivity of your measurement. Impossible? For a passive probe, yes. But you could try an active probe. Perfect. Why is it called an active probe? Well, because it uses active devices, transistors or FETs, for gain. Their design gives them high input impedance and low output impedance from DC to 1 gigahertz. Active probes offer the best of both worlds, filling our need for a minimum capacitance and maximum resistance probing device. Input Cs of 1 or 2 puff are common, while resistance is usually 1 megohm or more. And some active probes are 1x, allowing the highest sensitivity. How does it do it? Conceptually, a passive probe is simply a cable with an attenuating head connected to the input buffer of the scope. But an active probe is different. In effect, it moves the scope's input buffer all the way out to the tip of the probe and eliminates, as loading to the test points, the capacitances of the cable termination, and the scope. How? Active probes approach the problem of signal loading quite differently. The energy needed to charge these capacitances comes from the probe's amplifier, not the signal source. With an active probe, the circuit experiences very little loading at DC or at high frequencies. A typical active probe has an attenuator, a variable offset source, a high Z buffer to isolate the load from the source, usually an FET, a line driver, typically an emitter follower, a low-loss 50-ohm cable, and finally the scope input, usually 50 ohms or a 50-ohm terminated 1 megohm input. But let's look a little closer, starting with the FET front end. The FET is biased by a current source using low supply voltages, commonly plus or minus 7 volts. Now, what does that mean? It means the FET can't respond to any signal beyond those values. It becomes saturated, and its true linearity range may be only plus or minus 1 volt of input, which doesn't make for a very useful probe. Now, let's see what we can do about it. We could increase the supply voltages, but then the quiescent power dissipation would also shoot up, creating a combination FET probe and soldering iron. So what else can we try? How about a 10x attenuating tip? 10 volts here will now appear as only 1 volt at the FET. That's one way to extend the dynamic range. Another trick might be to add an offset voltage source to compensate for any DC level at the probe tip. For example, if we had negative voltage at the test point, we'd apply positive voltage at the offset. It's kind of a teeter-totter. Whatever voltage we have at the input, we plug an opposite voltage in the offset, balancing the latter. The FET gate stays in the middle at 0 volts. Thus, if we're looking for 1 volt AC riding a plus 10 volts DC, our FET bias could still be at 0 to give an accurate reading of only the 1 AC volt. Well, so much for theory. This is reality, a typical active probe, the Tektronix P6202A. Input R is 10 megohms, input C is 2 puff, bandwidth is 500 megahertz. Although the actual schematic might seem confusing at first, it's simply a realization of the functional elements and strategies we've just explored. Here's the probe tip, and this is the 10x attenuator. It consists of an 8 megohm tip resistance and another 2 megohms attached to the offset source. Here's the input FET, and there's the current source used to bias it. This is the emitter follower line driver. The offset source is generated and controlled by these potentiometers, which feed the offset voltage into the input attenuator. These form a teeter-totter with these two resistors, going positive or negative as necessary to cancel out negative or positive DC input voltages and to prevent FET saturation. Of course, there are other kinds of active probes. Electronic circuits are getting smaller and smaller. Use of fast hybrid subcircuits and surface mount components has created a difficult environment for probing, creating a need for an exceedingly small yet fast probe. Voila! This is actually an active probe. It has an exceedingly small replaceable tip for probing tiny components. It has the high Rin and low Cin required for high performance. Actual input impedance is 1 megohm, shunted by 1.8 puff. Bandwidth is more than 750 megahertz. It's designed to be mounted on a probe card for use in automated test systems. Under more conventional conditions, if you already know the DC element of your signal under test, you can use yet another kind of active probe, a variation on a 500 ohm divider probe. Here's the 500 ohm divider circuit itself. What we've added is a built-in variable offset. When we set that offset voltage to equal the DC potential at the probe tip, the current through the tip resistor goes to 0. Now, low current through a resistor implies a high value resistance. In other words, our probe has negligible loading characteristics for that voltage. We can attach this 50 ohm probe to active circuits without unbiasing them. All the measurements we've made so far have been with respect to ground or single-ended. Often we need to measure the voltage across a circuit element neither of whose ends are at ground. Or we may need to observe a difference signal under the presence of masking common mode signals, such as hum or induced EMI. You could use 2 matched probes and a differential plug-in, or try a 2-channel oscilloscope in its A-B mode. But the best way to do this is with a different kind of active probe. A differential active probe. What makes a differential active probe different? Let's take a look at a model of its action, a simple op-amp circuit. Signals common to both inputs are rejected, while the difference of the signals at the A and B inputs is amplified and output. The ratio of the rejected signal to the amplified signal is the common mode rejection ratio, or CMRR, a figure of merit for differential systems. On our probe diagram, the output is VA minus VB, with gain as a constant function of these resistors. As I said, you can try two passive probes with the differential plug-in, or use the scope's A minus B mode. But you must be careful that each probe is properly compensated and of the same cable length and characteristic. Otherwise, your signal of interest may be buried by minor differences in the probes themselves. A difference between the probes of as little as 1% in response will limit your differential accuracy, or CMRR, to only 40 dB. Passive probes, active probes. If both are correctly suited to your oscilloscope, when do you choose one instead of the other? That depends on your signal and circuit under test. Remember, at higher frequencies, active probes do a better job of isolating the circuit under test from the scope. This isolation reduces circuit loading and allows the truest representation of the signal. The high input resistance and low input capacitance of the FET prevent DC loading, high frequency loading, and signal amplitude loss. And the low capacitance gives you the best rise time possible. And some active probes are 1X, allowing you to see very small fast signals riding DC levels with minimal circuit loading. So, how do you know which active probe to use? We're back to considering the oscilloscope specifications, the special needs created by your circuit and signal under test, and the probe specifications themselves. Bandwidth, attenuation, input R, input C, rise time, and maximum non-destructive input voltages all have the same meaning as for passive probes. Remember that exceeding the maximum non-destructive input voltage may damage an active probe's internal circuitry. Other specs, such as input dynamic range, DC offset range, and tangential noise, are new. Input dynamic range lists the maximum AC input voltage that the amplifier in the probe can accurately reproduce. DC offset range gives the maximum value of DC voltage that can be compensated for in the circuit under test by the probe's offset circuit. And tangential noise is a figure of merit for the probe's amplifiers. It establishes a noise floor below which measurements cannot be made. What have we covered in this section? Well, here are some key points. First, remember that passive probes cannot provide both high Rin and low Cin at the same time, which is exactly what some measurements require. For those applications, an active probe is your best choice. Second, remember that active probes have their own limitations in both dynamic range and DC offset range. If you exceed either of these specifications, you will get a saturated, invalid result. Some elevated potential or high amplitude measurements can only be made with passive probes. And third, carefully consider your test point impedance, not only when you choose a probe, but also when you choose a test point. A high Z test point may not tolerate the 500 ohm DC loading of a low Z probe. A high Z probe may also fail because the test point's high R source and the probe's high Cin will form a low-pass filter which may degrade rise time or bandwidth measurements. By anticipating the effect of attaching the probe's input impedance before you attach the probe, you can prevent some unpleasant surprises. If you expect the probe's impedance to be a problem, try to find a lower impedance test point instead. Often the same signal will appear in many places on the circuit at the same time. For example, pick a transistor's emitter as a test point instead of its base. And if that isn't possible, you will need a probe with as high an Rin and as low a Cin as possible. You will need an active probe. So far, we've taken a look at passive probes and active probes, and we've taken a look at just a few of their many applications. But no matter how versatile these devices are, there's always another problem. Take the design of switching power supplies. This is a switching transistor. It controls current through this coil. A typical question, is the transistor exceeding its power rating? Easy, you say. To calculate power, you multiply voltage by current. Easy if you have the right tools. First, how do you determine the voltage? Well, you need to measure voltage across the transistor, not to ground. That's right, differential probe or similar strategy across the transistor from collector to emitter. Great, but now how do you measure the current? Okay, you could try measuring the voltage across an existing known resistor and derive the current since I equals V over R. Or you could insert your own resistor into the circuit. Of course, there are problems. If the resistor doesn't have one end at ground, you'll need another differential probe. The capacitance loading of, say, a 10x probe could change the high frequency characteristics. The value of that existing resistor must be known very accurately. Any deviation will directly throw off all your other measurements. And adding resistance might lock up the circuit anyway. Or you could use a current probe, like this one. Current probes convert flux fields to voltage signals by transformer action. So to measure the current flowing in a conductor, we surround that conductor with a magnetic circuit and capture some of its magnetic field, converting that field to voltage by transformer action. The transfer ratio of a current probe is specified in so many volts per amp. By dividing the observed voltage by a transfer ratio, we obtain an answer in amps. All Tektronix current probes use a single-turn primary and a multi-turn secondary transformer, with the single-turn primary being the wire under test. The basic sensitivity of the device is determined by the turns ratio of the transformer and the load placed on the transformer secondary. Part of this load is the cable and the cable termination, which can also change the sensitivity. As you probably suspected, there are several kinds of current probes: AC only responding, AC and DC responding, fixed core, and split core. This is a split core. I can open the core to surround the wire. It's a more convenient but less sensitive design than a solid core. You can increase split core sensitivity and extend its bandwidth by using a current probe amplifier. Fixed core current probes call for a little planning because you have to pass the wire through the core. For example, we can open this circuit and then insert the wire and probe in series. Usually, fixed core probes are permanently attached as calibration sensors, for example. AC only responding current probes operate by simple transformer action. The problem with simplicity is that they have a low frequency as well as a high frequency roll-off. Although AC-only probes are derated at extreme high and low frequencies, this design can feature fast rise times, high bandwidths such as 1 gigahertz, and low circuit loading. AC and DC responding probes have a little bit more of an interesting design. In addition to the passive current transformer, we add a Hall effect device for the DC and low frequency AC components. The frequency response of the Hall effect section is carefully matched to the frequency response of the transformer section. As one rolls down, the other rolls up. Their summation is a flat frequency response from DC to about 50 megahertz. Part of the Hall effect output is also fed through the transformer section to cancel the DC flux field. This avoids saturating the transformer in the DC and low frequency range. Just like voltage probes, before you can select the right current probe, you have to know some things about the characteristics of the signal under test and be able to match that to the probe specifications. For repetitive signals, you need to know the maximum AC current continuous wave as well as the frequency. Current probes are bandwidth limited just like all other probes, and their ability to withstand current degrades with frequency. Remember that current probes operate by converting the circuit's magnetic field to voltage by transformer action. Current probes are sensitive to DC content because it shifts them up in their magnetization curve and could reduce their signal accuracy through core saturation. If the signal is a single-shot pulse or low duty cycle, then you'll need to know its maximum peak current, also the pulse width, the rise time, and again, does it have a DC content? Once you've analyzed your circuit and signal characteristics, you're ready to select your probe, or at least examine current probe specifications. Many of them are immediately familiar because they're the same as for passive or active probes. Major specifications for current probes are bandwidth, rise time, input current rating, DC and peak AC, which derates with frequency, maximum peak current, and the amp-second product. What, you may ask, is an amp-second product? What does it sound like? For example, if we have a pulse input with an amplitude of 1 amp and a pulse width of 1 second, the amp-second product of the waveform would be 1. Why do we want to know the amp-second product? How does it relate to other specs? The input current rating for DC plus peak AC establishes a limit below which any signal may be handled continuously. Above this amplitude, continuous waveforms are not allowed. But single-shot and low repetition rate pulses may be, provided they do not exceed the amp-second product. Above the maximum peak current, I should add, no signal is allowed. The amp-second product is a measure of the energy contained within the waveform. The probe's amp-second product specification is a limit of the energy it can handle before saturation degrades its accuracy. That limit should not be exceeded when measuring single-shot pulses. Note that input impedance is still a concern even for current probes. By transformer action, current probes magnetically couple another circuit to the circuit under test. When we attach a typical current probe, we add a series impedance of about 10 milliohms shunted by 6 microhenries. Now that is a significant difference between current and voltage probes. Current probes add a series resistance inductance to the conductor under test. Voltage probes add a shunt resistance capacitance to ground. Sometimes this factor of series instead of shunt loading is a good reason in itself to select a current probe over a voltage probe. As with voltage probes, minor specifications may become important for your application. They include maximum hardware volts, a safety consideration, system delay, split or fixed core, probe size, and maximum conductor diameter, or how big a wire can you get a hold of with this probe. This AC-only responding current probe, for example, has a rise time of 350 picoseconds and a bandwidth of 25 kilohertz to 1 gigahertz. Its insertion impedance is only 1 milliohm shunted by 6 microhenries. A typical AC and DC responding probe runs DC to 50 megahertz with a rise time of 7 nanoseconds, aberrations of plus 5%, minus 5%, and 7% peak to peak. It's capable of measuring to 20 amps DC or DC plus peak AC and a single shot pulse peak to 50 amps. Now that we've covered abstractly things you shouldn't do with a current probe, let's examine some of the things you can do anyway. Cheating is an engineering term for bending rules. In this case, we'll cheat to extend the input range of your probe. For example, if the DC signal component is saturating your probe and derating your AC current measurement, you can wind coil wire through the core and apply voltage to generate another field with opposite flux to cancel the effect of the DC and avoid saturating your probe. You pay for cheating in other ways. In this case, I've introduced unpredictable parasitic elements into the measurement system that may become significant at higher frequencies. A second example, how can you measure a 50 amp signal with a 20 amp probe? Well, you could build a shunt pair with a 9x resistance ratio. Only a tenth of the current, 5 amps, will flow through the probe. Nice idea. Yes, but you have to know your resistances exactly, or we directly throw off the measurement, and the low-value resistors you probably need are usually not high-accuracy parts. Or you could not cheat at all. This monster here is another current probe. It uses a transformer to step down the input current to a level measurable by a second current probe attached to it. And that happens something like this. Now we can capture currents flowing in really large conductors. Using this probe, currents up to 700 amps RMS can be safely measured. Passive probes. Active probes, current probes. What have we discovered? I think the most important thing is that we're dealing with a measurement system, not just a series of isolated problems. The connection between the oscilloscope and the circuit under test is extremely important. How we get that signal to the scope's inputs directly affects the accuracy of our measurement. Do we need to use a probe? Well, the answer is probably yes, we do. The exceptions would be DC or very low frequency signals where a capacitive loading is not a consideration, or 50 ohm systems that can be terminated directly at the scope input. And even then, a probe is probably a handier, more convenient tool. But the big question remains, what kind of probe? Tektronix makes about 40 different probes, and they're developing more all the time. And there are good reasons for every one of them. Remember that probes don't exist in isolation. Consider the characteristics of the circuits and signals you'll be testing. Consider the specifications of the oscilloscope. If you match them to the probe specifications, you'll select a probe that will enhance the capabilities of the system and not degrade it. Most people look at bandwidth and rise time and just stop there, but that's only part of the equation. As we've seen, there are many different kinds of probes, each with some feature or specification that makes it the best possible choice for some particular application. Consider their specifications in light of your application. Here are some general guidelines for you. High Z passive probes are most effective for general use. They use high resistance to reduce DC loading effects on the circuit under test. They're very good for amplitude measurements. And only at higher frequencies could their relatively high capacitance become a problem. Remember that high Z passive probes should be compensated before use. Low Z passive probes are especially effective for high frequency and rise time measurements. They add much less capacitance than high Z probes. Their limitation is that their relatively low resistance may offer a ground shunt, distorting the signal under test. The effectiveness of both kinds of passive probes is enhanced by selecting low impedance points in the circuit for measurement. When that isn't possible, active probes are the best solution. They offer high resistance and low capacitance to the circuit under test. Proper ground lead use is crucial to most voltage probe applications. And finally, some measurements can be effectively performed only by current probes. Hopefully, I've introduced a few concepts that will improve your measurement techniques. Probe selection and use are neglected topics, and many important considerations are anything but obvious.